As we continue in Chapter 2, we'll be dealing in the second lesson with the idea of something called differentiability. That's a great word for hangman if you're ever playing that game. Differentiability. Differentiable is a subset of that word. It's connected to derivative, and if something has a derivative, we say it is differentiable. So we'll be talking about that today in Lesson 2. We'll learn about what it means to have differentiability. We'll look at what it means to fail to have differentiability. There's a test there, kind of like failing the vertical line test. There's a test for differentiability. And then we're going to work on some graphing today and how to graph both a function and its derivative function. All right, what does it mean to be differentiable? Most of the functions we encounter in calculus are already differentiable. You can tell because a graph is unbroken, it is smooth, and it has a well-defined slope at each point. It will not have a corner, a cusp, which we'll talk about what that is, a vertical tangent line, or it will not have any points of discontinuity. Okay, so you are looking for an unbroken, smooth function with no corners, no cusps, no vertical tangents, or no points of discontinuity, no asymptotes, no jumps, no gaps, no removable discontinuities, no discontinuities within their domain. So, if a function does have a corner, or a cusp, or a vertical tangent line, or it does have points of discontinuity, we say it is not differentiable. So it's either is differentiable or it is not differentiable. So let's talk about that. This is an example of a function that is not differentiable. Okay, continuous? Yes. Okay, this function is continuous. There are no gaps or removables or asymptotes. So this is a continuous function. Differentiable? No. And what makes it not differentiable is that it has a corner right here at the origin. And so the corner at x is 0 is what makes it not differentiable. So that's an example. Continuous, yes. Differentiable, no. Here's another piecewise function. We have two functions connected to each other. We have a cubic function here, x cubed, which comes up and connects to the origin. And then we have a linear function with slope 4 for 4x connected. Okay, continuous? Yes. Okay, the limit from the left and the limit from the right approach each other, and there is a value at f of 0. So we would say the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x, and that's equal to f of 0, and they are all equal to 0. So continuous, yes. Differentiable? No. And again, it's not differentiable because there's a corner where the cubic connects to the linear function. Okay, there's a corner at x equals 0. Here's the word cusp. A cusp is where the limit of the slope approaching different sides are both infinity or negative infinity. So here we've got a function approaching a vertical slope, and this is called a cusp. It's two curves meeting each other. So this is continuous again. Okay? It's not broken, but it's not smooth. Okay, in order to be differentiable, it has to be both smooth and unbroken. Okay, so that means it needs to be both differentiable and continuous. So this is not smooth, It is unbroken. Okay, there's no broken parts to it, so it is continuous, yes. Differentiable? No. Okay, because of the cusp at x is 0. Here's an example of a vertical tangent. Okay, if a cusp is where you have two curves meeting, here is it is smooth. Okay, this is continuous. This is all smooth. It is continuous, but we have something called a vertical tangent. That's where the slope is straight up and down, just for a moment right there. All right, and then the slope on this side. Okay, where the slope, if we could zoom in on that piece right there, right at the origin, it is straight up and down, just for a moment. That is called a vertical tangent. And so this is again an example of where it is continuous, yes, but differentiable, no, okay, because there's a vertical tangent at 0. Now, if it's not even continuous, if it's broken, then it's for sure not differentiable. Okay, but the examples we just looked at, they were all continuous, but they just were not differentiable. A good way to think about differentiable functions is that we say that they are locally linear. Now, to linear means it looks like a line. Locally means in a small area, okay, a small region, a small neighborhood, that it looks like a line. Okay, so if you were to use a graphing calculator and to zoom way in, the curve will look straight. So it will not look curved anymore. It will look like it's straight if you can zoom in far enough. That way you would know it would be also differentiable. So here's an example of a function. It's very curved. Okay, there are a lot of curves to it. And the question is it differentiable? Well, we look. Do we see any corners? Do we see any cusps? Do we see any vertical tangents? All right, are there any places where it is straight up and down? So let's look at the origin here. If we can zoom in on this enough, okay, it's never straight up and down. So it doesn't have a vertical tangent. Okay, so it looks like it's differentiable. Another spot that we could zoom in on, let's erase this part. Okay, let's zoom in on this spot here. Okay, so let's take a look at that. In fact, this screen right here has zoomed in on that spot for us. Okay, well, let's zoom in on this spot. Okay, so we could zoom way in on that. In fact, this slide over here has done that. And if we zoom in on that, this starts to lose its curved nature. It doesn't look like a curve anymore. It looks like it's pretty much a straight line going all the way through. Okay, there's no curve really to that anymore. And so that's another way that you can tell if a function is differentiable. If you could zoom in and it would lose its curved nature and start to look like a line. So here's a clear corner. Let's zoom in on the origin. Could I zoom in far enough that I would lose this corner? And the answer is no. Okay, no matter what, as far as I zoom in on this, there will always be a corner at the origin. I can never be close enough to where that corner would be straight. Okay, the farther I zoom in, it is still a corner. And so this will always have a corner, therefore it will always be not differentiable. Here's a cusp. Okay, could I ever zoom in enough to where it would look like it was straight? Okay, well, this cusp piece is coming down to the origin here. Okay, if I keep zooming in, no matter what, even if I'm zooming in far, there is still a cusp. Okay, the farther I zoom in, I could never make this look like a line. And so we would say again that this is not differentiable at that point. If it has a derivative, okay, that is called differentiable. Then it is continuous. Okay, you see the if and the then? So if differentiability comes first, then you know, you're guaranteed that it will be continuous. Okay, if differentiability comes first, that means it's already past the fact that it is smooth, it has no corners, no cusps, no vertical tangents, and no brokenness, no points of discontinuity. So it is discontinuous. It is continuous. But the other way around, if f of x is continuous, and then if your then comes, then f of x is differentiable or has a derivative. Okay, if that's the order of the if-then statement, that is false. Okay, it might be true, but it's not guaranteed to be true. We just saw 4 examples where it was continuous, but it wasn't differentiable. It was continuous because there were no gaps or removable discontinuities or asymptotes, but they weren't differentiable because they still had corners, cusps, or vertical tangents. So that may or may not be true, and if it may or may not, then we call it false. Okay, so make sure that you have the order of that correct. Now, there's a relationship between a function's graph and the graph of its derivative. We can learn things about the original function and about its derivative by graphing them. So let's practice that a minute. So here is a function, and we know it's a function because it passes the VLT. This function is continuous, but it is not differentiable. Continuous, yes. Differentiable, no, because it has 2 corners. The corners happen, I'm going to kind of divide this graph into pieces. So there are 3 pieces of this graph. So when you are going to draw a derivative next to it, you're going to want to kind of make these imaginary lines, okay, these are going to be imaginary, along the same section. So I'm going to make a line at -1, and then I'm going to make another line at +2. And I'm going to graph the derivative over here. Now remember, the word derivative means slope value. So let me look back, and in fact I think I'm going to add some imaginary kind of lines to help me out on the edges as well. So let me go back, and at -4 I'm going to put another line, and then at positive, oh, it looks like +4. Okay, between these 2 yellow lines, from -4 to -1, the slope is up 1 over 1, rise 1, run 1, rise 1, run 1. Okay, I'm counting the slope, and that's up 1 over 1. So the slope is 1. So when I go to my derivative graph, which is next door, between those same 2 yellow lines, I'm going to draw a value of 1. It's just a horizontal piece, and I'm going to draw the value of 1. All right, between the next 2 sections, between -1 and +2, this rise over run, oops, okay, is 0 over 1, 0 over 1. The slope is 0. So then I'm going to go next door to my derivative slope, and between the same two boundary lines, between -1 and 2, I'm going to draw a slope of 0, a value of 0, which is just along the x-axis. And then between my last two, between 2 and 4, so between those two, my slope value is down 2 over 1, down 2 over 1. And so the slope there is -2. And so I'm going to go over next door to my derivative graph, and I'm going to draw a value of -2, which is like that. Those three pieces of the slope value, okay, that was a slope value of 1, a slope value of 0, and a slope value of -2. Okay, those are marked out on the lines. Okay, so now I'm gonna get rid of my imaginary lines that, whoops. Okay, I'm gonna get rid of these imaginary pieces. Okay, erase those, don't need them anymore. I'm in a different app, I'm not in Notability, so it's not quite as easy to erase them as it is in Notability, but I'm gonna get rid of those. And to finish up the graph of the derivative, okay, there we go. I erased a little bit more than I wanted to. There we go. Okay, to finish up the graph of the derivative, I'm going to add some open circles to show that this is discontinuous. So there is a jump discontinuity at -1. There's another jump discontinuity at 2. But then the front and the beginning and the end are closed circles. So that is how you draw the derivative or the slope. Okay, use those sort of boundary lines to help you divide that up into different pieces. So let's practice that again. Let's go the other direction. Okay, let's go opposite. So this one only has one broken piece. Okay, the broken piece is happening here at 0, so I'm going to draw a line, which I'll eventually erase, okay, at 0. I need to draw a continuous function through 0, 4. So let me put 0, 4 here. All right, this piece on the left has a value of -1. So that means when I draw my picture, I need to draw something that has a slope value of -1. Not just a value of -1, but a slope value of -1. That means that on the left side, these are the points that will connect that line, because these points have a down 1 over 1, down 1 over 1, down 1 over 1. They have a slope value of -1. On the right side, these have a value of +1. So when I draw my graph, when I'm creating the graph, I need to create something that has a slope value, not just a value, but a slope value of +1. So that means I'll be going up 1 over 1, up 1 over 1, up 1 over 1. So then I'm ready to erase my imaginary line that I was using to help me kind of split my graph into two, and then I can connect the dots, and I have now drawn a graph of an absolute value graph that fit the requirements of the derivative graph. So this is going the other way. So you'll have a chance to practice this. I would like you to do it, please, on graph paper. There's graph paper in the handout module, or you can turn your Notability into graph paper. If you turn your Notability into graph paper, make sure when you submit it that you choose the option of background on, because otherwise when you submit it to me, all of the grids are erased and I won't know that you had those turned on. So make sure you have the background turned on when you decide to submit in Notability. Otherwise, use the created graph paper I made for you in the handout modules. If you don't, then I'm going to put a comment back to you in Canvas, and you won't get full credit. You'll get partial credit for not using the right graph paper. Okay. All right. We'll come back together on Wednesday morning and talk about Leibniz's approach to a derivative, and then how you graph these derivative functions and what it means to be continuous and differentiable. All right. So good luck with that, and I'll see you on Wednesday morning.